So we are going to do some physics review here. I'm going to be going fast through some of this stuff. So anytime you need to pause, take a better look at what's on each of the slides, please do. But if I actually go over everything here, it will take forever. So I'm going to try to make this as short a video as possible, but please review the notes afterwards as well. Okay, so let's first just talk about what we started with in the physics unit, and that's all about motion, okay? So first thing that we went over was uniform motion. So that's just something that's traveling at a constant rate in a straight line, right? Same distance over time. And when you look at the distance time graph, it's a nice straight line like that. And then we looked at average speed, okay? And that is when we have this uniform motion, so then we have a nice constant speed. So that is just your distance traveled divided by the time that has elapsed, okay? Another way we can calculate average speed is by figuring out the slope of a line on a displacement time graph. Make sure it is a displacement time graph, right? So this could be x1, y1, and this could be x2, y2, right? And then you can find the slope from there. So let's go over one example. We have a huge ocean wave or tsunami travels a distance of 4 times 10 to the 6 meters, 33.6 times 10 to the 4 seconds. Okay, so calculate the speed of the tsunami. Remember, speed, v is just distance divided by time elapsed. And we're given both of these. We don't need to do any conversion or anything like that. So we have 4.0 times 10 to the 6 meters divided by 3.6 times 10 to the 4 seconds. Hopefully you know how to put scientific notation in on your calculator. So that gets us 111 meters per second. Now remember, another thing you got to do in physics is pay attention to the significant digits. Here we have 2 and here we have 2, so our answer needs to also have 2. So I'm going to put that as 1.1 times 10 to the 2 meters per second, okay? If you need any more help with significant digits, things like that, how to put things into scientific notation, I'll go back and look at those lessons again. All right, and then let's look at speed time graphs. So we know uniform motion on a speed time graph is something like this, where it's just a straight horizontal line. Anytime you have a slanted line, that means you have acceleration. Okay, so acceleration is happening here. This is nice constant speed, okay? Right here where there's a horizontal line. If I want to know the distance that this is traveled when we have a speed versus time graph, I can find the area here underneath all here, and that area will tell me the distance that's been traveled. Then there's scalar versus vector quantity. So remember, scalar is how much but no direction, and then a vector is how much and in the direction. So scalar is what we just say is magnitude, vector is magnitude and direction, okay? So pause the video, go over these 8 things, see if you can remember which is scalar and which is vector. Okay, you paused, you promise? Acceleration is a vector. We care about direction there. Displacement, also a vector. Distance is a scalar. We don't care about this direction there. Energy, that's when people forget that is a scalar. Force is a vector. Speed is a scalar. Time is a scalar because we only go one direction with time. And velocity is a vector, okay? So let's talk a little bit more about velocity. So like I said before, if you have a position time graph or displacement time graph, then your slope is going to be the velocity, right? So you choose your 2 points on the line, and you can find slope from there, okay? Or if you don't have that, you can just do displacement over time. Just remember, it has to be displacement, not distance, and displacement is very different. Okay, another example. An airplane flying at a velocity of 900 kilometers per hour west travels 400 kilometers west. So remember, west means we're going to be going or making it negative. Okay? If you remember, we were going to look at our orientation. Here's north, here's south, here's east, here's west. North and east are your positives. South and west are your negatives. Okay? So I have a velocity of negative 900 kilometers per hour and a displacement of negative 400 kilometers. So I'm looking for time. When I look at my velocity equals displacement over time equation, I need to solve for time. So what I'm going to do, I'm going to first get time out of the denominator. I'm going to multiply both sides by t. Okay, that cancels that out. We get t times v is equal to the displacement, also not what we want. So then we are going to divide this side by the velocity, this side by the velocity, because therefore it cancels out, and we are left with an equation that we can use, which is t is equal to displacement over velocity. Okay, displacement again was negative 400 kilometers. Velocity was negative 900 kilometers. Okay, in our answer we want 3 significant digits. A negative divided by a negative is a positive, which totally works out because time shouldn't have a negative on it. Okay, so what I get there is 0.4 continuing. So to make that 3 significant digits, I need 0.444. No need to round up. Okay, well that was kilometers per hour. Those cancel out, we are left with hours. So 0.444 hours. And it doesn't say what we needed it in, so I'm going to leave it at that. If we needed minutes, we'd times that by 60. If we needed seconds, we'd multiply by 60 again. Acceleration is just the change in velocity during a specific time interval. So that remember that on a position time graph like we have here, if you see a position time graph curving like this, that means there's no uniform motion, okay? It has to be a straight line if it's a uniform motion. It's you also know it's accelerated motion on a velocity time graph if it's not flat. If it's slanted, that means it's accelerating, okay? And remember, acceleration is your change in velocity divided by time. So if I want to do another example of that, we have a racing car accelerating from rest to a speed of 55.6 meters per second east, so that is a positive direction, in 6 seconds. What is the acceleration of the car? So remember, acceleration being change in velocity, that means final velocity minus initial velocity divided by time. Okay, so here our final velocity is 55.6 meters per second because that's what it's speeding up to. Its initial velocity was 0 meters per second because it accelerates from rest. Okay, divide that by the time, which is 6.00 seconds, and we get, and also, by the way, we're looking for something with 3 significant digits, and that is 9.26 continuing, so that looks like 9.26666666 keeps going. So if I want to round that up to 3 significant digits, that'd be 9.27, and we got meters per second squared as our units there. Okay, so there we go, there's acceleration. The next thing we talked about in physics was work. And that's, remember, when a force moves an object through a distance, it does work. So it's just force times distance. Do you guys remember what is required for work to be done, though? The force and the distance have to be in the same direction. Okay, so if I'm lifting something, if I'm holding something up, I'm applying a force upwards, but if then it's moving sideways, then those are not in the same direction, okay? So now we're going to go over energy and how work is related to energy. So remember, types of energy, ones that we didn't necessarily go over. Nuclear energy, that's energy stored in a nucleus. Solar energy, obviously energy stored in the sun. Chemical energy, the energy that's given off through chemical reactions. Electrical energy, which is basically just a bunch of electrons moving around. And then ones we did go over, potential energy and kinetic energy. Remember, potential energy is energy that's stored. We did define stuff like elastic potential and chemical potential energy, but then one we have a formula for is gravitational potential energy. And remember, that's EP is equal to mgh, where m is mass in kilograms. G is your acceleration due to gravity, 9.81 meters per second squared, and h is your height in meters. And remember, this is all in your data sheet. You don't have to memorize the formula, don't have to memorize 9.81. Let's do an example of potential energy. We have a 55 kilogram diver standing on a diving platform. Gravitational potential energy of 5.4 times 10 to the 3 joules. I want to note that vertical height. So I know EP is equal to mgh, and here I'm actually looking for h, so I need to isolate it. So in order to do that, I got to divide both sides by mg, because that cancels it out there. And we get that height is equal to potential energy divided by m times g. Okay, so again, my potential energy was 5.40 times 10 to the 3 joules. I'm going to divide that by mass, which is 55.0 kilograms, times g, which is always the same, 9.81 meters per second squared. Please, you guys, please put that denominator in brackets. So when you're typing this into your calculator, you're doing 5.4 times 10 to the 3. Then you're dividing that, and then you put a bracket and put 55 times 9.81 and end the bracket there. Okay? And that gets you, well, we need 3 significant digits, but isn't this nice? It's just 10.0. And that is meters. That's all we're looking for. So there we go. There is the height that they dove from. Okay. And then we went over kinetic energy, which is just the energy that something has when it's moving. Okay. Still in joules, and your formula is right here, which again is on your data sheet. Okay. M is mass, V is velocity, mass is in kilograms. And velocity has to be in meters per second. So if you ever get kilometers per hour, you have to convert it to meters per second. Okay? Let's do an example of that. We have a small toy car moving horizontally at uniform speed, 2.2 meters per second, and has a kinetic energy of 18 joules. So now we need to calculate the mass. So again, here's our kinetic energy formula. And here I need to isolate the mass right there. So how do I do that? First, I multiply both sides by 2 because it's the opposite of multiplying by 1/2. Technically, you could be dividing by 1/2, but it's the same thing, you guys. So I get 2ek is equal to mv squared. I'm looking for m to be all by itself, so I'd need to divide by v squared. A lot of people think I need to do something with that squared. That squared only applies to the v, not to the m. So if you divide by v squared, you are done. You're good. Okay? So here we get that mass is equal to 2 times the kinetic energy divided by the velocity squared. All we got to do. So 2 times the kinetic energy, which is 18 joules, divided by 2.2 meters per second squared. And keep in mind the answer needs to be 2 significant digits because that's what we get in the question. And we get 7.4. That would be kilograms, okay? And the calculator gets 7.438, blah, 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 blah. But again, I only need 2 significant digits, so I just look at the 7.4. After the 4 is a 3, so it does not need to be rounded up. So there we go. There is the mass. for that question. And then we went over mechanical energy. You guys remember mechanical energy? So that's basically the sum of kinetic energy and potential energy. Okay, that's all mechanical energy is. Just take the kinetic energy at a point and the potential energy and add them together. Okay, so remember, usually we went over situations where mechanical energy was constant. Okay, so that means mechanical energy here is the same as mechanical energy down here, but it's just being added in different ways, right? So at the top here, it has lots of potential energy, but really low kinetic energy. So maybe the potential energy is 10 joules and the kinetic energy is 0 joules, right? But maybe down here, the potential energy is 0 joules and the kinetic energy is now 10 joules. Right? So it still ends up being 10, but we just get there in a different way. So that's what we did for conservation of energy, saying the potential energy at the top is equal to the kinetic energy at the bottom. Okay? So here we have a 1.5 kilogram rock. So that's its mass. Okay? Dropped over the edge of a cliff, 30 meters above the surface. So that's the height. We want to know what's the speed of the rock just before it strikes the surface of the lake. So it looks like we have enough information to find the potential energy. Okay, and then we need to find the kinetic energy. But we know that potential energy at the top here is equal to the kinetic energy at the bottom of this rock's fall. Okay, so there's two ways to do this. Just find potential energy by going mgh, and that's equal to your kinetic energy. Okay, but I want to just use this thing because a lot of you guys forgot that you could do this, and it's actually a bit of a shortcut because we know since potential energy at the top, which is mgh, is equal to kinetic energy at the bottom, that's equal to 1/2 mv squared. Okay, and then from here we can just solve for velocity. And because we have m on both sides, guess what happens when I try to divide both sides by m? They both cancel out. So in these questions, you don't actually even need mass, okay? So what I actually end up getting is that GH is equal to 1/2 v squared, okay? So if I want to rearrange that for velocity, multiply both sides by 2, okay? 2gh is equal to v squared, and then to get v, we just square root both sides. Okay, so that means velocity is equal to the square root of 2gh. Okay, if you don't like this method, you do not have to use it whatsoever, but it actually is a bit of a shortcut, and I don't even need to worry about mass. So if you get good at using this kind of situation or this technique and know when to use it, right? Know that when we're talking about something that's going from its highest height to its lowest height, that's when you can use this method. Because then here I only need the height. I do not need the mass whatsoever, even if it gives it to us. Okay? Okay, and so that gets me 24.26, but how many significant digits do I need? I have 3 there and 3 there, so I need 3, which gives me 24.3 meters per second. And there we go. That's my velocity. Okay, and finally, we went over things like systems and laws of thermodynamics and stuff like that. Okay, so remember systems, you can have open, closed, or isolated. Open exchanges everything. Closed can't exchange matter, but it can exchange energy. And in an isolated system, you can't exchange anything with the surroundings. The first law of thermodynamics was you can't create or destroy energy. You can only transfer it from one form to the other. And the conservation of energy is the total energy, including heat in the system and its surroundings, remains constant. Okay? So those are pretty much saying the same thing. Then your second law of thermodynamics is heat always goes from hot to cold. Always. It will flow naturally from hot to cold. Never naturally from cold to hot. Okay? So remember, there's some energy when we're trying to get something to do something. There's useful energy and there's energy that comes out anyways that's not as useful, right? So when you light a light bulb, the useful energy is the light. The not useful energy sometimes is the heat that always comes off with a light bulb, okay? So the initial source is called the energy input. So with a light bulb, that would be your electrical energy. The desired energy is called the output, okay? So whatever the output is just the work that the machine is supposed to do. So if we're talking about a light bulb, it's in the name, you need light, right? So anything that's not giving off light is not useful energy output, okay? So we use that kind of concept to calculate efficiency of different systems, okay? So remember that's just useful work output divided work input. And then we just change that into a percentage by multiplying it by 100, okay? If you're ever worried about that, remember, you can't have over 100% efficiency. So if you get over 100%, something's wrong. You probably need to switch your output and your input, okay? You probably have the wrong numbers for that. So output should always be smaller than input. We got a bunch of different energy sources, so just know that energy can come from all these different things, right? So we got wind energy, water, biomass, fossil fuels, and then non-solar is from geothermal and tidal, okay? And some of those are renewable, like solar, wind, water, only if the water is recycled, right? If you're using the same water over and over, then it's renewable. Geothermal, so that's basically just using heat that comes from the core of our earth. Tidal, that's basically the water in the oceans and the tides and stuff like that. And biomass, which is plants and things like that, that of course we're planting again and again and again and again. Non-renewable is stuff like nuclear, because we only have so much nuclear fuel source, and fossil fuels. Okay, so that is the physics unit in a very small nutshell, okay? So good luck with studying for that.